It's on, just so you know. All right, everybody ready?
On the slide.
Yeah. So welcome to the session for after lunch break, in which we'll have fluid power vehicle challenge, EPS pump demo, and wave energy harvester. And at end of 20 minutes of your presentation, not end, but towards 20 minutes of your presentation, I will raise my red pen, making you aware there's 20 minutes and you have 2 minutes to wrap up to be on time. All right. So with that said, you have a few seconds and I'll just raise my red pen raise my hands to get you started. Go.
So we are the NFPA Fluid Power Vehicle Challenge team for MSOE. We have Daniel, Mike, William, and Ernesto.
I'm a technical lead, and I will just talk about the project statement. So, the NFPA Challenge undergrad to build a fluid power vehicle, fostering teamwork and strict expertise for specimen engineer efficient hydraulic propulsion systems that overcome inherent energy losses and heat buildup to prevent machine wear. So I'm going to talk about a bit about the objectives. The objective is to create that we have vehicle sorts that we is to create a new vehicle design with custom made frame. We also want to place top 2 in every race, endurance, sprint, and efficiency. We want to run away the awards for the best pneumatics, best control / electronics, and we also want to have the safest design. I'll go briefly to the background research we made. First is last year's design. They made a tricycle with pneumatic and seat adjusters, and they had all the hydraulic components situated in the front of the rider, and they had all the pneumatics behind the rider. Some considerations they had after they finished their design, they had a lot of chain issues, and that's something we took into consideration. They had a leak flow in the system, so we also have to take that into consideration. And they have a rigid frame that was they had insufficient rigidity of the frame, so the frame ended up failing at some points. We also talked about this. We also looked into Sunny Polytech's Institute's 2025 design, and that design had a twin tank reservoir, 0 back accumulator drain, and a separate region pump. This separate region pump allowed them to perform especially well during the race. They also had a check valve after pump to stop backfeeding, which is due to back pressure, and they had shorter hoses to minimize the losses. Some consideration they had is since they didn't order any components ahead of time, they should have gone with a backup plan just in case the components didn't arrive in time. We also looked into FSU College of Engineers 2025 design. They had a backup reservoir that's situated below the rider. They had a pocket valve, which they said it was better than their school valve. They also had an additional filter, which helped them win safety awards. They had a compact manifold, which allowed to reduce the size of the overall bike, and they had prototypes created before the actual assembly. Well, some considerations they had is that they should have had better communication with each other as a team, and they did to know when to settle down on some of the improvements and when to improve on some other stuff, because they did do a lot of testing and changes. Outside research, we did research on human power vehicle challenge safety standards. We found out that a vehicle must be able to brake within 20 feet when going 50 miles per hour. The vehicle must be able to turn within 26 feet radius, and they must be able to travel 100 feet in a straight line from 3 to 5 miles per hour.
This is where I'll introduce myself. I'm Mike Rose. I'm specializing in frame design for the vehicle. A little about design concepts and selection. We actually started with 12 design concepts. We won't discuss all 12 for the sake of brevity of the presentation. But to rank them, we set up a decision matrix where we categorized on ease of fabrication, safety, performance, durability, uniqueness, cost. Up in the top row here is all the weighting factors that we put for all those. So we took each design. So let's say just for one, we'll take the slingshot. So you rated everything 1 to 10 on how we thought it would perform, meeting these criteria here. So say for safety, the slingshot scored an 8. So we multiply that by the weighting factor of 0.2. All those got summed in the rightmost column. Our top 3 designs are the workman's cycle at number 1, the slingshot at number 2, and the standard bike at number 3. A little more detail on those. The workman's cycle, if anyone's been in a manufacturing environment, the brand is actually called Worksman. We just use Workman, so it's a little different. It's essentially an extended frame tricycle with a rear deck for carrying tools, parts, whatever it be, across a machine shop or manufacturing environment. So we would have the benefits of the pre-built safety rated frame. We do have to integrate pneumatics as part of the competition. So our idea for this one was going to be some sort of air ride seat ram that we could adjust the pressure so it would set different heights for different height riders and it would cushion the ride a little bit. It used pre-built bicycle style steering, so we wouldn't have to design steering, but the problem was it's a very high center of gravity with how high you have to sit up. And it's a very low accumulator mount, which for hydraulic systems, your accumulators where you're storing your energy, you want that to be high up so you have gravity storing the energy as well as the pressure in the accumulator. Design concept number 2, which is closest to what we have right now for our finalized design, which we'll talk about later, is the slingshot. It's a 2-wheel in the front, 1 in the back. It gets its name from the Polaris slingshot, if you guys see those, where it's 2 wheels in the front, 1 in the back. Key feature being recumbent style seating. It's easy to mount components because it's just a basic ladder frame. We can run diamond plating across, we can run sheeting across, we can run crossbars if we wanted to mount components. And it left that open and it would be fairly easy to fabricate, so it'd just be cut, notched, welded tubes. The drawbacks are the weight being constructed from steel tubes and a long distance between the pump up at the front here as labeled in the top and the motor at the back here, which allows more hydrodynamic energy losses in the hoses. And then our third top was the standard bike. This actually utilizes a frame from, I believe, 2 years ago. It's a lighter frame design than the others we've discussed because it's only 2 wheels. It would be the easiest to fabricate, scored very highly in that category because it's already built. It'd just be a matter of altering and adding different hydraulics. The only problem is being all the components mount above the rear wheel and you sit high up, it's a really high center of gravity and that can lead to stability issues, especially at low speeds, which means we need to get it built earlier so we can actually practice with it before competition. And it's not a very unique design. Most teams end up going with a standard tricycle or a bike like this. And we wanted to be different. We wanted to do something new. So we have this design based in the image of, think like a race car roll cage tube chassis, just simplified and scaled down. So it's a single driven rear wheel, kind of like the slingshot design. The hydraulic components go on this raised rear deck here. And then it's going to have a pneumatic system, which Daniel's going to talk about later, on all 4 corners of the vehicle. A wide front end for extra stability. And then because there is a safety award, we're looking to win that by implementing a full containment racing seat and 5-point racing harnesses as well. We did a quick FEA analysis on the frame to make sure that it would not fail during competition. So some of our research on human-powered vehicles, which, funny enough, there's more documentation about the ASME human-powered vehicle challenge than there was on this competition. And the real main difference is that we use hydraulics, they don't. So a lot of the research plays through, and a lot of teams cited sources saying that if a frame could statically hold a 600-pound vertical load and a 200-pound side load at the same time, that it would be safe for your worst case scenarios of driving. So think hitting potholes, heavy cornering forces, all of that. So we did this in SolidWorks simulation because while ANSYS is the industry standard, was being designed in SolidWorks. So by the time you do it in SolidWorks and then you draw the line body in ANSYS to match and simulate, it would have just taken too much time to iterate. So we did it all in one place. So you can see here we have the loads applied. I had to do it as 2 separate because you can't do component loads very easily in SolidWorks. So I did 2 separate ones. And then as far as fixturing goes on it, we fully fixed the front spindle mounts. These 2 right here, these are where rod ends are going to go where the front spindle mounts to. And then we fully fixed the mount for the single rear wheel. We could have done remote displacements to the center of the front wheel, but it didn't change the numbers significantly, so we just kept it simpler with the fully fixed. As far as results go, we have an overall factor of safety of about 2. So you look at the green range and the von Mises here. This is our key stress point, is where these 2 triangulations meet and where these front wheel mounts are. And those are in that factor of safety of 2 region. There's one failure point at the rear wheel, which anyone in FEA would know. If you have a fully fixed support, the stresses get way artificially ramped up in fixed support regions. So we kind of had to neglect that and use engineering reason to say it's good enough for what we're doing. The thing is that uses 1/4-inch plate. The previous design that actually used the rear wheel that we're using for this is reused from a previous year, and that was mounted to 1/4-inch plate, and it survived all of testing and competition. So because that was proven to work, we could neglect that in the FEA given the boundary conditions.
So my name's William. I was the hydraulic specialist for this team. So here's our manifold circuit, or our complete vehicle circuit design, and a detailed diagram of the manifold. Some notes on this. We'll get into the drive modes in a second and what all the solenoids do. but we added a needle valve to dump our accumulator when it's charged for safety reasons. We have 2 test points. Part of the competition is them screwing in a test point and seeing if our pressure readings are accurate. And then we have the pump motor, which we'll get into later as well. So when none of the solenoids are charged, these 3 valves, we have a direct drive mode. This is making sure that it fails safe. So if we lose electricity mid-race, it'd be capable of continuing. We have the pump that's pressurizing the line, going through the check valve, and then powering the motor, and then just straight draining out to the reservoir. Secondly, part of the requirements for the challenge was to be able to store energy. So we have our accumulator up here, and then the pump will, with these 2 solenoids charged, now supply pressure to the accumulator. And then we have the accumulator discharge mode. So when we need to use the energy stored in the accumulator, we only charge this single valve, and then the pressure from the accumulator will go back through the motor and then drain out. We won't be able to pedal during this unless you're able to pedal more pressure than the accumulator, but that is unlikely. So we have the check valve there for that. Then to meet a requirement for regenerative braking, we had to model the motor as a pump in Automation Studio. But what would occur, and it didn't simulate completely correctly, but what would end up happening is that a suction line would occur from the drainage, go through this check, get stopped there, and then all the solenoids are charged and suction to the through the motor, and then charge that accumulator that we're storing energy. And then lastly, we created a what we call a kidney loop filter mode. So part of the safety requirements of some of our pumps and motors is having a filtered system, not having contaminants in the oil, because hydraulics is very sensitive to that. So we wanted to include it in our system, but since it's a very low pressure, low flow system, including it could sacrifice efficiency for races. So instead, we included it in a separate line. And what would happen is between races, between testing, we would activate this solenoid, and then it would just feed flow through the filter straight to drain. And the kidney loop is just flowing the oil through, filtering it, and heating up the oil as well.
All right, well, as previously mentioned, I'm Daniel. So basically, for our bike, what we want to do is have a pneumatic system that lifts up the bike. So the only purpose is not to use during competition, but more as a showcase thing and for ease of use. So basically, what it's going to do is you're going to have 4 different cylinders on each corner of the bike. And it's going to be able to lift the bike up about 4 inches so that you can either store it, work on it, or kind of just get out of the way. Like I said, we don't plan to use it while the vehicle is moving, so I'll come into in a second. But this is just the general schematic. We did do it on Automation Studios, which is basically a circuit software. So here we're showing the lift. So basically what's going on is over here we have a pump, but in our case it's going to be a reservoir that we pre-charge with pneumatics or air. It's going to go through a needle valve, which will be a lockout tagout valve. So basically when we're not using it, we're actually going to lock out and tag out it, just so that if we're riding the bike, we're not going to actually hit a button, the bike lift up while we're taking off. So that's something we consider there. Then we do have these valves here that will open and close. To allow the actual pneumatics to lift and close. And we can show you guys the close position now. So as you guys can see, the blue is the air getting out and it's going out here. And these do show that they are manual. However, they will be automatic in when we build the bike. It will be the button we press. And then now we're going to sizing the pneumatics. So kind of how we sized it. So we kind of just used a simple force equals pressure times surface area. So we were given the fact that the bike had to beat a maximum weight requirement of 210 pounds, so it cannot go over 210 pounds. And then we do have a max pressure of 100, I believe it's 150 psi, but we kind of toned it down to conserve factor of safety. So from there, we were to get our surface area and then convert that surface area to diameter. And we ended up being a diameter of 1.64 inches for our bore size. And we ended up rounding that up to 2 inches just to increase our factor of safety once again. From there, like I said, since we aren't using it during the actual competition, the only time we're going to be using it is while the bike is at standstill. We do plan to just put air in the reservoir and then have it basically be pre-charged so we can lift the bike up and down. So we were able to get our reservoir sizing by getting the volume, the amount of air volume of each cylinder and then multiplying it by 4. So we got a total volume of 5.27 inches cubed, which we convert to gallons to be about 0.22 gallons, so almost a quarter of a gallon. So that would lift the bike once to its maximum height of 4 inches. However, we do want to be able to do that multiple times. So just in case we want to lift it all the way up or not all the way up, we ended up going with a 1 gallon tank just to have the ability to do it over and over again. So based on our calculations, we should be able to lift the bike up about 6 times at maximum height.
For our pump and motor selection or for the hydraulics, we decided on a 4cc gear pump and a 5cc axial pump. Gear pumps are better for low pressure, high flow situations, and the axial motors are better for high pressure, high flow systems. We chose specifically a axial piston for the motor side because axial piston pumps and motors are more efficient at high pressures than gear pumps motors. And so we wanted to make sure that we're making our system efficient. And part of having an axial motor is you do need to actively filter the system. But then the axial piston was chose for the motor side because efficiency matters a lot more than the pump side. And the gear pump was specifically chosen over an axial piston pump because it's around 3 times lighter than having 2 axial piston pumps and motors. And then for the gear ratios, so this is kind of the most important part to the hydraulic system, was making sure that we can shift gears and be able to pump the right amount of pressure and flow to make our bike function. So the main thing that we looked into was using a pinion gearbox. Other groups have seen success using the gearbox in past years. Sunny and Utah used it last year. They used the P112. We're using the C112. It's slightly smaller and has slightly smaller gear ratios, but it still has the same amount of gears. So it allows us to have a very wide gear range of 0.55 to 3.30. And because this is a sealed system, we won't run into any issues with chain derailment, which is a common issue groups have had in the past. And it has a drive system integration, so the pedals are directly connected to the gearbox, and then you're able to shift between the gears, and it outputs the gear ratio. For the calculations, what we ended up doing is using a average optimal speed for cyclists, which was 70 RPM. And what we did is we took that 70 RPM and then saw how much it took to reach certain pump RPMs, or the gear ratio required to reach that pump RPM. And then the pump RPM determines the pressure in the system from the hydraulics handbook we were using. And from there, then we got our required torque input. With the required torque input, we were able to determine the pedal force required to go at that speed with that pressure, with that torque. And what was realistic, we thought around 100 or 150 to 200 range was optimal. And then that would output a different torque. But then we'd have a different gear ratio depending on, or these gear ratios were to optimize the output torque to pull force. Pull force, gravity, and friction. And then we determined a bike speed from that, which our numbers say we will be going a lot faster than previous groups, but we didn't take into account any losses, and it was an incompressible system with laminar flow.
And I'll briefly touch on the electronics controls that we use. We use the Innovation Mobile PLC and touchscreens. The specific mobile PLC that we use is the MC282-18-16, which has integrated valve controls, which allows it to communicate well with the hydraulics and pneumatics. It has 18 inputs that we can read the different digital signals that we are going to have from different pressures. And then we also have 6 outputs that we control all the different modes of the hydraulics and also control the modes of the pneumatics system. For the pneumatics, we're going to be using parallel connections. So the 2 front pneumatics are going to be connecting to 1 wire, so they're going to be used simultaneously. And then the back ones will be controlled at the same time as well. We're using a capacity touch, S50 capacity touchscreen, which can be connected by Canvas to mobile PLC, which allows you to quick connection between both of them, and they're able to just rapid, like if you touch the touchscreen, it sends an input, and then it's also able to get an output. We're using distance sensors and each of the cylinders.
All right, so now I'm going to talk about our first semester schedule. So first, pretty much the whole month of September was built on just getting background research and establishing the team. So we have to understand what we're doing, how we're doing it, and then do background research on other teams, see how they perform, and how we can use some of that as inspiration. Then from October to November, we were sizing. So there's a lot of calculations that went into sizing the hydraulic components for the most part. We managed a little different. And then from November 18th to now, we've been working on vehicle design and circuit creations for both pneumatics, hydraulics, and our actual frame. And then lastly, we're in the stages of actually purchasing components and preparing our presentations. We do still have to order some pneumatic stuff and a little bit of hydraulic stuff. And we do plan to get our bike frame done. If you want to go on the next one. Yeah, so our hard deadline is February 15th. We want to have our frame fabricated. So we are getting a company to help us build the bike. So they're going to be cutting and notching, and then we're going to help with assembly and maybe some welding, Mike. And then we do want to have our electrical system fully done, or I mean, in the most part done by February 21st, followed by hydraulic schematic with about 3 days in between, because these kind of go hand in hand. And then lastly, we do want to have pneumatics done by March 1st. There is a different deadline for pneumatics because component ordering time is different. And lastly, we do want to have the bike fully done by March 1st, so that we have a couple weeks before competition to actually test it, calibrate it, make sure things work. If things don't work, to pivot in another direction.
These are the sources that we use, the different like website that we use for the background research. And thank you for
Thank you, guys.
the representation.
Questions?
So you mentioned that you didn't model any of the losses. So what are some of the losses in the system that you could have modeled?
Some of the losses will be like the line losses due to the flow regime. Like if it's being turbulent or laminar, you can have different pressure losses along the lines. But typically those are pretty small. They range between, from what I can remember from my class, they range between 1 psi to 20 psi, depending on how long your line is. But typically, to be a massive line loss, you need to be like hundreds of feet to have a considerable pressure loss. Those are some of the losses that we can think of.
Yeah, and we plan on testing our systems by measuring pressure and flow output to RPM in, and that will give us a good estimate of overall system efficiency, which will include all those losses.
There's also the fact of driveline losses too in some of the calculations, because we're using mainly a chain sprocket drive system. So you pedal and then the gearbox would output a chain and sprocket to the pump, and then the motor would have a chain and sprocket to the rear wheel. And that's another thing that really isn't, especially if the sprockets are well aligned and you use the right lubricants and the right wheel bearing greases, there's really not a lot of loss in that system to the point that it could be deemed negligible as being a small percentage of the total power input.
So for your design, I see that you had this decision matrix and you had converse to a single concept. But thereafter, whatever you chose, was that based on some kind of rubric, like, okay, how well is particular component suited to your purpose compared to others? Was it more like based on prior team experience that you were guided by?
A little bit of both.
Yeah.
A lot of looking at what other teams did that was successful. A lot of looking what previous teams here did that was or wasn't successful, and trying to take as many good elements as we can. Like our top design choice was actually the 1 wheel in the front, 2 in the back, prefab frame. But then one of our main objectives was we wanted to make our own frames. Then we pivoted to the custom design because, you know, in our heart's desires, we wanted to make something completely new from the ground up. So it was a lot of what we wanted to do as a team versus competition rules versus successes and failures of previous teams.
Same question for hydraulic circuit. Was it like inherited from the previous team or was it completely new?
This is a completely new hydraulic circuit. We're using a different brand of valves, and we're using a different brand of valves, pump and motor. We're still using the same accumulator. And it was made new because the only hydraulic circuit in the basement intact used a separate pump for regen. And we did not want to do that because it requires a much more complex system that induced it had a pneumatic clutch to reverse brake, and that induced a lot more losses than they would have liked.
Any questions? Maybe I'll ask one more. How much, compared to your standard cycle or bicycle, if it's a trike or recumbent, how much more force would you have to apply with your design?
Ideally, not much.
Pedal, yeah.
Ideally about the same. So a lot of our pedal force data actually came from me in the gym on campus, measuring RPM and wattage on an exercise bike. And then we ran the numbers on that to convert to torque and all that based on pedal length, converting power to torque input. And then again, taking torque and the pedal length to get force. So the data we got for a cruising speed, like the two that we had highlighted as our main speeds, were what I would call mild effort. So like kind of leisurely pedaling your bike down the road. But if you wanted to really giving it 110% of everything I had as a man of somewhat average fitness, pushes us into like the next two where we're seeing theoretical speeds of 34 to 35, but that's also not to be sustained for a long period of time.
Then like the addition of the pinion gearbox should make it relatively similar to a normal bike because the gearing ratios is going to be a lot easier to pedal because we do have to build up enough power to beat that pressure, right?
Yeah,
So you use that gearbox to help pass that little hill. Should be cruising like a normal bike, or at least hopefully close to one.
Additionally, being a 12-speed, it's more than a standard road bike that you can keep in what your personal comfortable range of power and speed is for a greater range of vehicle speeds than a standard bike.
All right, any last questions? Not that we'll have around a couple of articles. Ask him to take over.
As I said, yeah, I don't know why. Then I get to my slides and I click and it's not moving forward.
No, it's because you right click.
I didn't. I was just using the scroll wheel the whole time.
I don't know. You accidentally like hit it, and we tried to move it. But
Yeah. Oh, I wonder if it got in the comments part. If it gets into the comment.
oh yeah.
If you're ready, Dr. Rice.
Be good.
Hi, everyone. I'm Tobias Landis.
I'm Alexander Lowe. I'm Blue Pillow.
And our project was the EPS pump scale model. Just to give a brief overview of everything in our presentation, we will start off with an introduction where we will go over the design process that we use for this project. Then we'll go through our project definition, which consists of our problem statement, and our product definition, followed by our product design and our SolidWorks models.
So the introduction, in order to guide ourselves for this project, we decided to implement Ullman's 5-phase design process to sort of act as a roadmap for this year. So we knew what to do for that year. With this design process, we first started with the project definition, which ultimately defines just the purpose and intention of the project. In our client EPS, they had a good understanding of what the project was. As a result, we simply needed to define what tasks and approximate roadmap or approximate timeline in order to complete the project. Moving on to the second phase, product definition. This pertained more so to what the project itself will be, just defining it. From this, we were also able to extract quantifiable engineering specifications from the client's desired features of the product. Phase 3, conceptual design. This entailed more so designing potential features of the product In order to create conceptual designs, this was done using morphology chart, gathering all those potential features into one location, making conceptual designs based off of that, and then ultimately creating a rubric in order to rate all of these potential designs and converge on a final design. The fourth phase of the project, product development, this entails to the generation and evaluation of the product itself. This is where we are currently at in the product. And at this point, the current actions we are working on is reverse engineering parts at the client's facility, CADing all of the scanned parts, which that's what we are doing to reverse engineer, and then ultimately manufacturing them and evaluating those parts to make sure that they adhere to the client standards. And then there is a fifth phase of this design process, which ultimately is inapplicable to us as the product that we are creating, the sole customer will be our client EPS, and it will not be mass produced, and therefore it is not relevant to us. Moving on into the project definition, the first phase, this ultimately defines the overall purpose of defines the project itself and correspondingly the purpose. And it was EPS Pumps has no physical model to showcase at trade shows and career fairs the types of pumps they specialize in repairing and improving through aftermarket modifications. EPS Pumps would like a functional scale model of a ring section multi-stage pump that adheres to the API 610 BB4 standard for display at future trade shows and career fairs.
So the next phase of the design was product definition. So when at the beginning of the semester, we met with EPS Pumps, and we asked them a few questions because the project was kind of open-ended and we wanted to specify and know what we should focus on. So the first one was, is there any specific scale ratio that EPS would like for the pump? What type of pump does the client want? What are the maximum allowable dimensions of the pump? Should the model be able to be disassembled to inspect interior components? Are there any other companies with similar products to compete with? Does the client want any deliverables beside the model? And does the client want the pump to actually be functional? So we deployed quality function development. We created a list of questions and features that we wanted EPS to give their opinion on and weigh the importance of each feature. So this is the table that I created with features on the left and the customer weighting on the right side. The customer rating was on a scale of 1 to 15, with 15 being the most important and the most desirable, with 1 being something that was more flexible and that they were not going to be as picky on. So the constraints that we settled on were the scale model must fit in a box that is 2 feet by 2 feet by 3 feet. The scale model must weigh less than 40 pounds, must be able to be disassembled for transportation and serviceability just in case something breaks or a bolt comes loose. They need to be able to fix it very easily. And a budget of $1,000 for the overall project. This was provided by MS with $80,000, but the client showed interest in providing more money if needed. So we started with researching similar products, which was a little unusual in our case, because the project is very unique and that no other companies have scale models of the pumps that they work at, that they work on. So the closest product / competitor is the actual pump that we are scaling down, which is KSB HEC 57 boiler industrial pump, which is shown in figure 1. This is an image taken right from the KSB website. So we also looked at patents, and like I said, our project is unique in that we're not building a brand new product, or more reverse engineering a current product. So violating patents is not a large concern because we wouldn't have to work around any existing pumps or scale models that are currently manufactured. Instead, we saw patents more as a guide, because patents show the purpose of a product, how it's manufactured, and we used patent EP3A2, A4, 419A1, which describes a similar multi-stage centrifugal pump. Figure 2 is the image as shown on the patent, and figure 3 is the cross-section that was provided to us by the client. There's a lot of similarities between them. The biggest one that we focused on, I guess the biggest piece of information that we got out of the patent was the manufacturing process and how the pump is held together. The patent focused on 2 types of ways, which included using tie rods, which is one long rod that ties the ends of the pumps together to keep everything secure. And the other alternative was bolting each section of the pump instead of all the components at once. And we came to the decision that we would design tie rods for our scale pump.
In order to not violate any rules laid out by government institutions and to just make sure we are following best practices, we also did research on codes and standards. And similarly to the problem statement, we mentioned that this pump must adhere to the API 610 standard and more specifically follow the EV4 type pump, which describes a horizontal ring section multi-stage pump. Another code and standard that we use was the ASTM 52920 standard, which just describes additive manufacturing for the production of parts. We deemed that this code and that the standard would be useful as we are ultimately looking to create a scale model using additive manufacturing or 3D printing, and we want to make sure that we can follow just the best guidelines in order to repeatedly create quality parts so that different parts weren't of poor quality than others.
Over the semester as a group, we visited the client's facility in which we adhered to OSHA standards such as wearing proper facial protection as in safety glasses and steel-toe boots for our feet. And the next standard we follow is ASTM standard, which relates to packaging and shipping test standards. Our product is going to be moving a lot since it's going to be going from the client's facility to trade shows to career fairs. It's going to be traveling a lot. And we wanted to make sure that it gets there safely and correctly. And the main focus that we took with the ASTM standard was related to draw testing the product, because the product will be moving in and out of vehicles and on top of tables and people holding it. And in the case that it does fall off the table, or someone does drop the product, we have to ensure that it will operate even after being dropped and it won't fracture and the product will be fully functional despite falling from a height of the table or someone's waist from carrying it.
So next we're going to move on to product design and how we went about designing our scale model. So first we start off with our morphology chart. Since we are reverse engineering an existing product, our categories focus on modifications that would have to be made to the pump after we scale it down to turn it into a presentation piece. So the first main category that we chose to focus on was visibility. How are we going to showcase the interior of the pump? The main parts that we want to showcase are the shaft as well as the impellers and diffusers. And we settled on three potential ideas: a 180-degree cross section, showcase the shaft, the impellers, and diffusers across a flat plane. Next design we considered was a 90-degree cross section, very similar to the 180, but this time this would showcase the impellers and diffusers more inside the pump instead of being more exposed as opposed to the 180. And the last design we considered for visibility was the extended window, just a small window in the front where people could look inside and watch the parts in motion. And the next category we considered was safety, specifically most pumps in like factory settings that they're not worried about rolling over. They're just way too heavy. So, but for our pump is going to be on a table, so we have to make sure it's secure and won't roll off. So we consider three potential ideas: a flattened bottom, the suction heads. One of them has a rounded base. We consider just flattening it off. Second, because that was extended supports that would go to the ground, probably just stay there loosely. And then the last idea was potentially bolted to a base, or we could bolt the pump to maybe a skid or some other base to give it that stability. And then the last quantifiable thing we considered was ergonomics, ways to help transport this pump as it moves from facility to facility. The three ideas that you consider were handholds, basically insert handholds at the bottom where people can grab it, handles at key locations, whether it's the ends or the sides. We left it up to the person that took this design, and then grip extensions where people could have a firm place to grab it, maybe on the side as well. So for our conceptual designs, each of us took some of the ideas from the morphology chart and added any new ideas if necessary. This is my design. I went with the 90-degree cross section, the flat base at the bottom, as well as handle grips at the bottom of the base. Another idea I had was potentially including extra components that people can pick up and hold when they're at the EPS table.
So the second design is my rendition of it. I decided to go with the 180-degree cross section for the most visibility, while also being able to keep the pump stable. I have a grab handle on each side of the pump. There's only one is illustrated here, but there will be one on the other side for a total of 2 handles. I have 2 support legs on each side, and just like the handle, there's 2 on each side for 4 in total. And I went with a 5-stage design, and we ended up choosing a 5-stage design for all of our pumps instead of just being unique to mine.
As Alex mentioned, the third design also maintains that 5-stage design compared to the 7 stages of the HDC 57 uses. Beyond that, the modifications made to the pump is the leg and flange mounting method that would utilize something such as a skid or a base plate to mount both the legs to, and then ultimately pull the pump to. Beyond this, other modifications made were a side inlet while maintaining the top end outlet, and then using the extruded window in order to keep the interior components such as the diffuser and color.
So next, we developed our rubric for how we're going to rank these designs and choose the best options. So we assign each of them a scale out of 10 points, either being 0, 5, or 10, based on how well each of the designs performed in their respective category. First main category was visibility, and we awarded points based on what percentage of the impellers and diffusers can be visible, whether it's all of them, half or none, and if there's any other value, we would just best approximate to cater to either one of these. We gave each category a scale factor based on the client's responses to the QFD, as well as giving a weighting ratio that was calculated based off the scale factor that will be used in our decision matrix for determining which design had the best out of each of these categories. And the second category was safety. Again, out of 10 points. Safety means not only considers the potential of the pump rolling off the table, but also pinch points, and do people have large enough space to operate inside of it if they need to repair. These were the most important categories. They have the highest scale factor of 15, again from the QFD, and the same weighting ratio. Next thing we consider as aesthetics. This is a bit more qualitative, a metric, but we felt this was important to include to make sure that to keep in mind that parts need to be distinguishable from one another, and it needs to be easy to understand and follow. And so we assigned 10 points based on simplicity, and we gave a scale factor of only 10 for this one because we felt it wasn't as important as the first 2. Next category is ergonomics. This correlates directly to the handholds and other alternative grab surfaces that people will need to transport it. We gave it 10, 5, 10, and we gave it a scale factor of 10 as well. Even though it is important, safety and visibility are the 2 major concerns for this project. And another category we considered was weight. The hard constraint was to be less than 40 pounds, but we don't want to try and meet that. We want to try to exceed that by being under 20 pounds. We think this will make transportation very easy, as well as just being easier to handle, and also it increases safety if it's potentially dropped on somebody. And then the last one was serviceability. This is the ability for the pump to be assembled and disassembled if repairs need to be made or cleaning needs to be done. Essentially, this extends the lifespan of the pump, so we sit on a scale back to that as well. And this is just a simple weight calculation for determining the weight factor for each of the categories. We took the scale factor for each of them and divided by the sum of the scale factors. So just a simple example for visibility, one most important category is 15 over 76 for 197. And with all that, we created our decision matrix. We evaluated all 3 of our conceptual designs from the 6 categories. A few key things stood out after we went into the decision matrix. The first one being that design 3 struggled with visibility. With a small window, especially at a large trade show, there's going to be a lot of people crowding around. You don't want a lot of people trying to squint through a small little window. Design 1 did struggle a bit with safety, as just a flat surface on the bottom isn't as structurally sound as supports coming out to the side and increasing the surface area and decreasing the potential to roll over. And even with everything considered, we still felt there was maybe 1 or 2 things we could potentially add to the pump that we will get to very shortly. So what we decided to do is we decided to combine the best features from all 3 of our designs into one final design. And this is the final design here. We went with the 90-degree cross section. The 180 would provide a little more visibility, but what we felt that wasn't necessary because people are mostly going to only be looking at this pump from one side. As well as we felt that 90-degree cross section would give a better visual of the pump, of the components being inside the pump. And also 180 degrees does erase some potential structural concerns as these suction heads would no longer have support at the top. We decided to bolt it to a base, specifically a skid. Not only is bolting to a skid create maximum stability, but it also solves our ergonomics issue by creating very easy handholds that people can grab onto and transport. We decided to go with the extra components, like handrails, so not everybody has to look up at the pump at the same time. Some people can have components that they can look at as well. We also decided we realized that one of the shaft ends may be exposed, so a sleeve to cover that up may be needed for safety reasons. And even though this project is planning on being a functional project, that is not our deliveries. That is not in our deliverables for this year. We just need to provide a model and a scale model. But we still thought it would maybe be a good idea to have a crane where people can turn and see the parts moving in the pump.
Moving on to the SolidWorks model, which is where we're currently at, as mentioned in the introduction, we're product development. The ultimate assembly of how the pump works is we have a shaft with the suction discharge head at either end, and the assembly process goes as a case section, diffuser, and impeller. Then that gets repeated, and after all components are on the shaft, then we use the tie rods to ultimately sandwich everything together. At this point, we have scanned and modeled majority of the interior components. We have all case sections done, all diffusers done, but we're still in the process of modeling the impellers, which is why the assembly is a bit bare right now.
So as we wrap up the fall term, we're going to look ahead to the spring term and our goals. So like Luke said, we need to finish modeling the impellers because you can't make a pump unless we have all the impellers and the diffusers. So we need to finish that up. We're going to order parts and hardware, specifically the skid. We're going to be shopping on a MasterCard. That's going to be our main source of parts for the project. We're going to actually manufacture the pump, to manufacture the shaft, the impellers, the diffusers, the case. And then we're going to tie that all together once we have tie rods designed for the pump. Because since we're scaling it down, it's not going to be very easy to find long tie rods to hold the whole pump together. So we're gonna design those ourselves. We're gonna test the prototype by dropping it and performing FE analysis. We're gonna drop it because we need to see if it actually breaks, and we're going to find ways to improve that. Using FEA can also show some weak points when certain forces are applied and factors of safety for the shaft and the impellers. And finally, assembling and refining design, because the product is not going to be perfect the first time we do it. So there's going to be multiple rounds of iterations that we're going to have to perform in order for the pump to be functioning to the client standards and to be safe and to meet our standards.
Hey guys. Questions? Go ahead.
So, do you know what is the target audience for your customer when they use this demo? Is it engineers or is potential customers?
EPS. Yes, EPS specifically said they want this for churches and career fairs. So potential interns, maybe MSOE students, they probably potentially want to present this at our career fair, and at various trade shows, potentially other people who may potential partners that may want to view the kind of work that they do. They want this to help display the kind of work that they do. So maybe potential partners as well as future interns, engineering students, probably be the main target.
So it means that it doesn't highlight technical parts for the pump. Like you don't care the actual performance of that demo. It's more like just an overall mechanism display of how the pump operates?
Yes, the end goal of the project is to have a functional working model. However, EPS, our client is viewing this as a 2-year project, where our deliverables are to get them, are to fully scan and reverse engineer the pump, get fully model in SolidWorks, get a physical prototype of it, preferably 3D printing. And then once all of that is done, then a new senior design team will take over and they will go about making it functional.
Yeah, in your constraints, can you go to your constraints and specification slide? Is this a full set of constraint specifications or these are just the major constraints?
These are the major ones that we gather based on the client's responses from QFD.
Was the material not an important factor for the prototype? Did it need to be metal or ABS?
Not for our project this year. Obviously, when the new senior design team goes about being a functional part, material will have to be considered. We did talk about potential material, but considering we just want a physical display piece, we aren't worried about functionality right now. So material wasn't.
So it doesn't need to have any moving parts at all. It's just gonna be all solid.
We do want the shaft to potentially rotate if we had the crane. That's potentially with working with the client to add ball bearings to allow at least the shaft to rotate so people can see that.
You also talked about doing the FEA to model like dropping the prototype,
Yes.
right? Wouldn't that be an important maybe constraint specification for the project to drop it from 3 feet? That might be a good constraint to put on there.
Any other questions? Dr. Lapur?
Just one question. So for the SolidWorks model that we plan, do you have SolidWorks model by the way?
We have a partial assembly, yes.
We wanted to showcase this because these are the main components that we're going to be showcasing.
And then do you have like the weight of the machine? I know it must be less than 40 pounds, but how do you want to calculate the weight?
Well, we did experiment with prototyping some of the 3D printed parts, so we can kind of use the weight of these as kind of a metric scale to the entire model. Once we are limited on EPS schedule when we get into scanning and reversing parts. So once we have those, then we can start getting a better metric of the weights.
The final product must be, what material can you use in the final product? Like the 3D.
Yeah, it's 3D printed.
Even for the final one, the 2-year basis.
Yes, we're just getting EPS of physical prototype right now.
And do you have any calculation or any estimate of how much would you need to update the shaft to design the crank?
The crank is more of an afterthought right now. Currently, we are just focusing solely on reverse engineering and modeling all the parts that we scanned. We are not so much concerned about having a functional crank for working just having a crank for the non-functional version. Because the client is ultimately looking for deliverables this year, just to have the SolidWorks model itself, and then just a scale model to better understand what the final product will look like when it's made from the proper materials.
And considering the client will be working with us to add ball bearings to the model, he did not express any concern about required force necessary to turn it.
So you are using ball bearings.
Yes, to rotate the shaft, if we go with the crank.
Questions?
Did you gentlemen have any experience with scanning before you went to the UPS facility with the 3D laser scanner reverse engineering? That's something you had to pick up.
At least myself, I've had prior experience with mechanics-related products, so reverse engineering sockets. Beyond that, I've never used any scanning device like with the laser gun that we were utilizing.
I had no prior experience. It was a lot of fun.
What were your thoughts after you got a scan, model, then tried to model it in SolidWorks? What were your thoughts about the converting to SolidWorks? Was it a little more involved than what you were guessing?
Yeah. I thought we'd just immediately be able to transfer it right over.
Yeah, it's quite a process, so it takes a lot to get to wherever you are.
What's the biggest surprise of this project that one thing is like, oh man, I didn't think of that. Yeah, one thing that surprised me about this project and it's like, oh man, you think about that.
I will say one thing that at least was very surprising was the first time we toured the factory, just seeing the scale of these pumps. Yeah, it's definitely very surprising. And just the process of scanning the parts and turning it into SolidWorks. When you scan the parts, you take cross sections and you have to import them into SolidWorks, and then you have to try to match your sketch with the cross sections, map it out that way. But even then, there's still more steps. That process is definitely very surprising.
Are you planning to include any like tolerancing for the parts? Since you want the shaft to rotate, right? And the inner components, are you consider looking into tolerancing for the different components? Is that something-
Mainly for the shaft as well as the components of the fuses. Yes, obviously we're gonna have to have a better tolerance for like the hour diameter of the shaft and air diameters of the shaft and impellers, the impellers and the fuses.
All right, if no other questions? Next team to take over. Oh, you understand. Say. Yeah, oh, yeah, you can do. Okay, thank you. Bye.
Whenever you're ready, Dr. Bias.
Just let him depart, of course.
Right. Okay, so our group was the wave energy harvester. So I'm Colin.
I'm Jonathan. I'm Sean.
So we follow the Allman's mechanical design process. So that goes through the stages. So we got product discovery, project planning, product definition, conceptual design, product development, and finally product support. And we'll go through each of these as we get to them in the presentation. So in the fall term, we went through product discovery through conceptual design. And then in the spring, we plan to focus on product development and product support. So in product discovery, we identified the need, defined the opportunity, and established our goal for the project. So a little background on wave energy itself. Wave energy is a very consistent and highly dense renewable resource that remains very underutilized currently. So there's an estimated 29,500 terawatt hours per year for the exploitable wave power resource. And for reference, this exceeded the global electricity consumption in 2018. And we can see how wave energy compares to solar and wind. See from these graphs that it's much more dense and also much more available. Be available 90% of the time. But wave energy does come with some challenges. So it's a very low frequency, high amplitude form of power. So turning that into consistent power that can power a grid proves to be challenging. And then you also have to design for a harsh, corrosive marine environment. And then since so many of these wave energy converters are featured offshore, there's a high cost for installation and maintenance. So going on to our problem statement. So the growing demand for clean renewable energy highlights the need for innovative methods beyond wind and solar, with wave energy offering a highly concentrated yet underutilized resource. This project addresses that challenge by designing a safe, portable demonstrator kit that converts water wave motion into measurable electrical energy without turbines, serving as a reliable and educational tool for providing proof of concept for wave energy to electrical energy conversion. So in this demonstrator, we're mainly focusing on safety. So obviously having all electrical components being safe from the water, focusing on repeatability and reliability, because we need to engineer it for consistent performances across repeated demonstrations. And then practicality, so designing it for easy assembly and transport and durability to make it easier to use for said demonstrations. So some wave energy converter, or WEC basics. So the most common type of wave energy converter is the point absorber. So this is going to use the oscillatory motion of a buoy to extract energy from waves. So that relative motion between the buoy and some sort of reference, like a pulley, it's going to drive a power takeoff system, or PTO, and that PTO is what's going to convert that mechanical motion of the buoy into electrical power via a generator. And we can see on this graph on the right, this diagram, how it goes from the wave itself to the potential types of PTOs to the generator, where it eventually gets to the grid. Then as for modeling and the forces on these buoys, so the buoy is described in 6 degrees of freedom. So you have its surge, which is its motion in the X direction, and its roll, which is its rotation in the X direction. Then you have its sway, which is motion in the Y direction, and its pitch, which is its rotation in the Y direction. You have its heave, which is its up and down motion, and the yaw, which is its twisting in the Y axis. And it's going to be governed by the second law of motion applied to a rigid body. You can see the forces on the buoy in this graph as well. So you have the hydrostatic restoring forces from buoyancy. You're going to have the force from gravity on the buoy, the force from incident waves created, the added mass from the accelerated surrounding water, and then the PTO reaction forces, which act as both load and control input. And then maximum power out capture is going to occur when the buoy dynamics are tuned to the wave frequency. And some of the applicable codes and standards. So since this is like a scale model demonstration, there's less codes than would be for a full like actual wave energy converter, but we still do have some we have to adhere to. So the IEC lays out procedures for scale model WEC testing. So we plan to adhere to those for our testing procedures. And we're also going to use the IEC IP ratings to test like the safety against the water ingress for our electronics. And when designing our mechanical components, like our gears and fasteners, we're going to use the AGMA standards for gear strength, the ISO standards for gear accuracy, and then the ISO standards for the various fastener properties. Then we move on to the project planning stage, where we allocated resources, schedules, and responsibilities. Then we sequence tasks to align with academic deadlines. See that here in our Gantt chart. So we have the 4 main phases with the steps therein. Who the step was assigned to, the estimated start and end dates, and then the amount of days scheduled for each task. We can see in the fall term, we completed the project and product definition. We did the quality function deployment, QFD, and competitive benchmarking. Then we went and generated our concepts and then scored said concepts using a Pew matrix. And then for our leading concepts for your preliminary CAD designs. And we also completed some preliminary fabrication and informal tests to kind of get a feel of the feasibility of the project. And then in the spring term, we plan to do a detailed design of our final chosen concept. Also have to build a wave generator to have repeatable input so we can measure our efficiency. And we're going to do MATLAB and Simulink modeling of our PTO and buoy to optimize that geometry. And we're going to finally fabricate a prototype and follow that IEC style testing.
For product planning, we used QFD to translate customer needs into measurable engineering requirements. We captured expectations and we established benchmarks for evaluating all design decisions. Our design objectives were to demonstrate conversion of water wave energy to electrical output, to protect all electrical components from water contact for safe operation, to provide reliable and repeatable performance suitable for repeated demonstrations, and to produce a scale model system intended for educational demonstration. Our design constraints were that we could not damage the provided tote. We cannot use a turbine in the design. The design must contain a digital display of voltage, current, and power. The design must fit inside the provided plastic tote. The design must be safe to use, and the total cost must remain below the $500 budget. For our design targets, the assembly time should be 60 minutes or less. The conversion efficiency of input power to output power should be 75%. The device should not require repair or replacement before 100 demonstrations. The packed volume should be less than 1/10 of a meter cubed, and the percentage of additively manufactured parts should be between 50% and 75%. For the quality function deployment, or QFD, we translated the customer's needs into engineering requirements. We ensured that design decisions align with delight targets and discussed thresholds, and we provided quantitative framework for concept evaluation. The customer was asked to provide ratings for engineering features with the sum of the ratings equal to 100 to each analysis. 100 was chosen because there were 12 different engineering features. So in order for this customer to sum up to 100, they could not choose the same number for all of them. There had to be actual weights placed to them. The customer chose the two highest as reliable and repeatable performance and it being low volume. And the three least important were low cost, it being eco-friendly, and it being durable and rugged. We researched 3 different designs that are already on the market. The Core Power Ocean C4 had high power per ton. It had active control for storm survival, and it was modular and scalable for wave farms. Its weaknesses were that it had high system complexity due to the active control, and it was surface-based, which left it exposed to storms. The Ocean Power Technologies Power Buoy had a proven reliability in long-term deployments. It had a simple PTO with low maintenance, and it was ideal for niche markets. But it had a very low power output, and that made it not suitable for grid applications. Finally, the sea-based wave power park had exceptional survivability with the PTO being sheltered. It was simple and modular, giving a plug-and-play deployment, and it had minimal visual and surface impact. Its weaknesses were that it required complex subsea cabling networks, and the power collection infrastructure would add to system cost. We used the research and rubric from our QFD to compare the competitive benchmarks previously spoke of, based off the engineering features also defined before, with 5 being the best and 1 being the worst. We created 5 different measurable values to evaluate designs. They can be seen across the top underneath the arrows. The arrows show whether we want to maximize or minimize the value. We use the options above to show the relation of the measured value to the engineering features. A strong relation would be given an S and a rating of 9, and a average and weak can be seen below that. We summed the rating for each column in the previous slide to create a weight for how much each measured value would meet the engineering features. Then we compared what we could find for each of the competitive benchmarks to the measured values. Finally, we got delight targets and discussed thresholds from our customer for each of the measured values.
So then moving into conceptual design, we really want to focus on creating multiple solutions, comparing the alternatives of the compute decision matrix, and then selecting our top desired concept. So for the concept development, we kind of figured out the key features for a wave energy converter, which included the buoy placement, buoy shape, buoy limitations, force connection, force rectifier, generator type, and generator placement. And then we thought of a few options for each of these key design features. And then from there, we generate 9 concepts with a few options from each of these different key features to further analyze. Then we created a rubric correlating our criterias to rate our concepts. We defined metrics for measurable values for each of the concepts, with a score of high being the best, score of 1 being the worst. We used our delight targets and our discussed thresholds provided by our customer, Dr. Bias, to scale up these or scale the actual scores. From there, as a group, we created this Q matrix to essentially evaluate each of the concepts. As you can see, the criteria are here, and each concept was evaluated by our team based on what we thought and some of our research on what would be the desirable, the top idea for each concept. So we got our non-weighted scores below, and then we used the weight also provided by our customer, Dr. Bias, to get our weighted solution scores. We figured out that our top concepts were concept 2, 4, and 5, and we went to further analysis of those 3 concepts. So those 3 concepts, concept 2 was a cable and drum out of water generator. So this used a cable and drum connected to the axial flux generator along with a ratchet system and gearbox, and a torsional spring in the drum connected to the cable and buoy. So this concept had high reliability, easy maintenance, and waterproofing, and effective power smoothing, but required precise pulley alignment. Concept 4 was the rack and pinion underwater generator. So this concept had the permanent magnet synchronous generator along with a gearbox connected to the rack and pinion, which then connected to the cable, pulley, and then the buoy. This concept had high mechanical efficiency and compact footprint, but was kind of complex for waterproofing and maintenance of that underwater generator. Concept 5 was a direct shaft underwater generator as well. And this used a linear generator connected to those shafts and the buoys. The buoy could move up and down, and the whole system could rotate back and forth. So this concept was mechanically simple and had fewer moving parts overall, which reduced the transmission losses, but had a lower generator efficiency due to that linear generator and limited the adaptability of the wave conditions due to that restricted force or the restricted motion. So we decided on concept 2 as our best concept, which is what we kind of saw in the Pew matrix. So this involved a axial flux generator up here, which the axial flux generator was important because it was the best out of the 3 generators that we looked at for lower frequencies, so lower RPMs, and it was positioned out of the water, which made it safe from the incoming water. All the electrical components were safe. Then it connected to cable, drum, and ratchet. So you have your cable coming out onto the drum and then ratchet system that isn't completely modeled, but it's in that section. This provided a simple, scalable mechanism for the transfer of force, so it transformed that buoy, the linear or close to linear motion from the buoy into rotational motion that could be used in the generator to collect the power. And then a flywheel and gearbox were included as well, connected to the actual generator. And this addressed the challenge of transferring the kind of ununiform motion from the wave and making it more like easily, I guess, accessible, and increasing the rotational speed that we might need for the generator, because obviously we're seeing low amplitude. So we want to increase that speed for the actual generator. And then we had a buoy and free cable, which allowed for flexible motion to be captured through all the different wave energies and variation. For the justification for the selection, we did have that high Pew score of 398, which is that's why we thought this concept was the best. It had superior maintainability because it had that out of water generator, which simplified the waterproofing, inspection, and repair. Solved our core wave energy converter challenge with the flywheel and gearbox directly addressing the regular wave input, and provided educational value as this is very observable because it's all outside of the water and you can see the motion in the actual mechanism. So kind of going into further detail about this design, the buoy, which we ended up modeling it as a cylinder, could move up and down and connect to the pulley that would be connected to the bottom of the tote, and go up and then connect to the drum, which had a torsional spring inside that would kind of keep the tension from the actual cable. Then be connected to a gear train, which would then be connected to a ratchet system that would just ensure that the motion that is on the generator is just one direction. So we just want to make sure that it was spinning in one direction to collect that energy. Then some of the overall overall dimensions include the buoy, which we estimated to be about 75 inches cube. Cable was about a quarter inch diameter. The drum 4 inches diameter. Included a ratchet, then a flywheel with about 4 inches diameter, torsional spring, gearbox, generator, and then the overall dimension of the tow that had to be that the whole project could be included in was 36 at a depth of 36, a width of 21 inches, and then a height of 19 inches. So this is where it had to be enclosed in. Going over a cost summary of our project for the first semester, we spent about $175, which majority was from the axial flux generator that we got from our top concept. We saw this to be about $80, and then some other sensors, bearings, couplings, and then another DC motor, which a lot of those parts were used to create a wave generator, which we'll talk about later. But that was just to get consistent waves that we could use in our efficiency calculations later on. Semester 2, we estimate to spend about $110 to do a lot of parts already. A lot of that comes from the hardware for the actual wave energy converter, where we have such things as like stainless steel cable, Arduino board, and some other miscellaneous hardware. So we estimate to spend about $280 on this project. As far as feasibility goes, we have a high technical feasibility because we think the 75% efficiency is going to be a little bit ambitious, but we feel as we can get to that point through our design from low FT waves, and this overall project should be pretty durable overall because we are seeing not a lot of forces from those smaller waves. Economic feasibility, we see an estimated cost of $285, which is well under our $500 budget. So we think we should have a pretty significant cushion for next semester in case we incur other costs. For manufacturing feasibility, we want this to be 50-75% additive manufactured. So this is pretty achievable at MSOE because we have access to material extrusion printers, powder bed fusion printers, and that's resin printers, as well as we have access to the machine shop where if we do need to work with metal parts, we can work with metal parts. And then for testing feasibility, we have a plan set in place to validate all performance targets by using the IEC standards for our scale model testing.
The next phase of the project is the product development. And here we will conduct detailed design, simulations, and prototype fabrication. And we'll apply FEA dynamic modeling and component testing to ensure safety and reliability. Also, big lessons we learned from the fall semester. So the main one is that manual waves were not sufficient for repeatable efficiency tests. So that resulted the necessitation of the creation of a wave generator to make the waves, which we can see in this video here. So basically a DC motor drives a gear, which in turn drives a shaft, which drives these two cams, which push these floats up and down to create waves. And then it's also important to note that this was outside the original scope of the project. So the creation of this doesn't follow the design process completely. It just needs to work enough for testing. And then also literature introduced more advanced WC modeling methods, which we also plan to take advantage of. So yeah, the impact on the plan is we obviously are prioritizing this wave generator design, and then we're using MATLAB. We're going to use MATLAB and Simulink to refine the PTO and components. So the plan for the future work is, so we're going to do dynamic modeling. So we're going to do PTO modeling in MATLAB and Simulink, and we're going to use that to tune the gear ratios and flywheel inertia to maximize energy capture. And for mechanical design, we're going to use methods from the design machine components class for designing our mechanical components. And for the crucial components, we're going to utilize FEA to ensure safety under our estimated loads. Also do simulation and optimization. We're going to estimate wave forces using fluids coursework and additional literature. And we're going to explore basic control and optimization to try to achieve near optimal performance. And the final stage of the process will be product support, where we will deliver documentation such as an operating manual and demonstration procedures to ensure that the demonstrator can continue to be used. And we're also going to plan iterative improvements for possible future teams based on the feedback that we get. All right, so thank you.
Questions?
So very nice presentation. Congratulations. And the design is interesting. The only concern about the design I have, when I first saw you presenting it, is that have you considered like wild animals or like big plants like seaweed gets like jammed into those strings? And also like what kind of material do you plan to use for that cable? Because that is like a very crucial part for your buoy to operate.
Yeah, I think for that cable, we are gonna kind of lean towards like a steel cable, so some kind of metal, just to make sure it's strong enough and it's not gonna break away from some like waves or anything.
It's more than the mechanical, right? You also need to consider the chemical. Like,
Yeah, corrosion resistance, like. So yeah, we gotta look more into that, but yeah, making sure that's corrosion resistance obviously is very important, to make sure it's strong enough, so we'll look further into that, but. And then as far as like animals and kind of, I guess, plant life, this is like for a scale model, I guess it isn't as important, 'cause it's more for demonstration purposes, but if it was, I guess, put into like the ocean or some kind of waterway, then we would have to, I guess, create a method to actually, I guess, keep that cable safe, and then basically make like an enclosure for the actual, the whole wave energy like converter section where the generator would be placed in. So we kind of talked about potentially connecting this to some sort of like barge or some kind of like already like in place, like structure. Yeah, so like that could be set somewhere else, so it'd be like safe on some kind of rig, and then the buoy would be connected out. So the buoy would be pretty safe overall. It's just we'd have to worry about the rope. So we're not as concerned about that with our project, but in the future, if this was actually a real demonstration, real product, then we have to be concerned about that.
The questions?
Yeah, I mean, you say you're gonna do some modeling later on, but have you thought about what kind of forces you might be able to see? And how you're gonna scale those down?
So that's really why we're trying to prioritize the wave generator. It's like the thing to generate the waves, because right now we currently don't know what kind of waves we're gonna be able to get out of that. So once we get those, we'll be able to like actually estimate the wave forces. But right now, we really don't have a frame of reference for the types of waves we're gonna be able to get. So
Yeah, because we're trying to make that predictable with that wave generator, so we can see the consistent amplitude and frequency of those waves. So then we can use that to estimate what kind of forces we'll see on the buoy, and then using some of those, like the wave forces that we would like typically see those in that one slide, that we can kind of estimate what we would see from like on the buoy, and then kind of, I guess, send that along to the actual, the generator, like the overall drum.
Yeah, if we wanted to really simplify what the forces we're gonna see on the buoy, it's just buoyancy. But then, once we want to improve our simulation, we could apply like, we'd have to take into account the direction the wave's coming from. But we're trying to make it a unidirectional wave where it's only going like transverse or perpendicular to our buoy. That's the goal.
Yeah, you might wanna instrument your buoy with some sensors, right? So it can measure like acceleration and.
Yeah, we guys talked about putting 4 sensors on it, just try to see the acceleration. So I know, I don't know if you bought those or not, but we did talk about that. So we were gonna see like estimate the forces based on that. So we will consider that and probably take that into account for next semester. Any other questions?
Would it consider any like safety features in design, like if the waves are so bad, so it stops working and doesn't break, like that, like one like the reference?
Yeah, for this model, I guess we're not as concerned about it because it's more for demonstration purpose, but I know, because we looked at like the core power one. The core power one that was found in like industry, we saw that they actually, what they used was they used like pneumatic pistons on the inside. So if there was really harsh storms or really high wave amplitude, they would actually basically just kind of like lock these pistons up, or lock the pneumatic pistons up, so the buoy couldn't actually move as much. So that's how they did it. But that is one of the big concerns with wave energy converters, because these obviously they're being put on the ocean, and there's so many different conditions that can happen in the ocean. So you have storm, you can have super high wave amplitudes. So we're not as concerned about that, but in the actual industry, there are different ways and methods that they use to actually lock down the wave energy converters. So,
So, your question.
Yeah, so the real products that they make, do they just plop them in the middle of the ocean, or do they put them in places with high traffic, like in inland?
yeah, so but I like research the core power ones specifically. The like West Coast is actually where they saw more of the high amplitude waves. So a lot of the testing for them was on like the coast of Portugal, and then they're trying because they're like it's like a Scandinavian company. I can't remember Sweden or one of those companies, but they're trying to get into the US too, and they do have some testing along the Pacific coast, but there is a region where there is like peak amplitude waves where they want them to be, but it's usually typically on like the west coast of some kind of like any kind of nation.
Yeah, when you think about like thermodynamic cycles, you want to do like the same over and over again. And waves in the middle of the ocean aren't really the same over and over again. So there's a few locations on shores. I'm pretty sure there's some in Scandinavia that the waves are very consistent, and that's where we're starting with the wave, or that's where wave research is starting.
Any other question? Yeah, good.
I'm unsure like how, like, if it's really related to project, you guys are more doing a model, like, and it's gonna be building up wave energy a lot, like, it's gonna have a lot of, how is life expectancy, like, you guys have in like number of cycles, you have to be able to reach, or like a number of times that it could be run for.
Yeah,
It was 100 demos.
Okay, 100 demos, yeah.
Peak of overall.
yeah, it's the
Oh, yeah.
here we have to, ideally it was supposed to be made for 100 demos, and then obviously that scores less than 10 demos, but we want to ideally get at least 100 demos.
Sure, yeah. Thank
Any other questions? All right, if none, then hand it on. Thank you all for the time. Thank you. Rodriguez, Dr. Fulapur, attending and giving us insightful feedback. Sure, thank you.
Honestly, I think it's kind of a good idea. It's the midway thing, almost like breakfast.
Yeah.
We're talking about.